So far on our machine learning journey, we've covered supervised learning and unsupervised learning. Today, we begin to tackle reinforcement learning. But before we can understand reinforcement learning, we need to understand something called the Markov decision process,
Boring!
or MDP. So, what is MDP? And what is reinforcement learning? And what does MDP have to do with reinforcement learning? Well, let's find out. Welcome to Julia for Talented Amateurs, where I make wholesome Julia tutorials for talented amateurs everywhere. I am your host, the Dabbling Doggo.
I dabble.
According to the Wikipedia article on reinforcement learning is the area of machine learning concerned with how intelligent agents ought to take actions in an environment in order to maximize the notion of cumulative reward. Between supervised, unsupervised, and reinforcement learning feels the most like artificial intelligence. While supervised learning and unsupervised learning feel like a natural extension of data analysis and data science, reinforcement learning feels more like a natural extension of engineering, science, and social science. Reinforcement learning is an enormous field of study with a rapidly developing body of literature, so I will only be providing a brief glimpse into this world in this tutorial and the next tutorial. I hope to make a separate 13-part series dedicated to reinforcement learning at some point in the future. But before we can begin to think about reinforcement learning, we need to understand something called the Markov decision process. According to the Wikipedia article on Markov decision process, a Markov decision process provides a mathematical framework for modeling decision-making in situations where outcomes are partly random and partly under the control of a decision maker. MDP is an extension of the Markov chain, also known as the Markov process, which was developed by the Russian mathematician Andrei Markov in the early 1900s. According to the Wikipedia article on the Markov chain, a Markov process is a process for which predictions can be made regarding future outcomes based solely on its present state. And, most importantly, such predictions are just as good as the ones that could be made knowing the process's full history. MDP takes the Markov chain and formalizes it into a mathematical framework that may be used to make sequential decisions under uncertainty, where all of the uncertainty arises from outcomes that are partially random and partially under the control of the decision maker. MDP has been around since the 1950s and is used in many disciplines, including robotics, automatic control, economics, and manufacturing. By itself, MDP is not considered reinforcement learning. But MDP is the foundation upon which reinforcement learning is built, so knowledge of MDP is a prerequisite. Mathematically, MDP is a tuple, or tuple, containing 5 elements. S is a set of states called the state space. A is a set of actions called the action space. T is a transition function defining the probability of transitioning to each state given the state and action at the previous time. R is a reward function mapping every possible transition to a real reward value. Gamma is a discount factor that defines the relative weighting of current and future rewards. Don't worry about memorizing all of these elements. We'll see them again when we get to the code. This MDP is just a mathematical framework that defines a world where you can insert an intelligent agent. Once you've set up your MDP framework, the goal is to choose sequential actions that the intelligent agent can take in order to maximize the reward. So how do we solve this MDP in order to find those sequential actions? You can use various algorithms to quote-unquote solve this MDP. The algorithm that we're going to use today is called value iteration. The value iteration algorithm uses an iterative process in order to calculate the value for each state using something called the Bellman equation. The Bellman equation calculates the value of each state as the sum of an immediate reward plus the discounted sum of all future rewards. By using this equation, the value iteration algorithm can figure out the optimal values for each state that maximizes the reward. Based on those values, the algorithm can then generate an optimal policy that maps each state to an action. The policy is referred to by the lowercase Greek letter pi. The policy is basically like a treasure map that tells the intelligent agent how to move around in this uncertain world in order to maximize its reward. Having access to such a map could be extremely valuable, right? So, how do we get our hands on such a map? In the Julia world, we can implement and solve MDPs using the POMDPs.jl package. The POMDPs.jl package can trace its roots back to the early days of Julia, when Michael Kochenderfer was working at MIT's Lincoln Laboratory in 2012. He used an early version of Julia, with the assistance of Julia co-founder Jeff Bezanson, to develop code for a next-generation aircraft collision avoidance system to be used on all commercial airplanes. Michael Kochenderfer gave a fascinating presentation on the subject at JuliaCon 2017. If you haven't seen it yet, I highly recommend watching it. There's a link to it in the description below. Michael Kochenderfer is currently an associate professor at Stanford University and the director of the Stanford Intelligent Systems Laboratory. The POMDPs.jl package is a product of that lab, developed by a team led by Zachary Sundberg, who was a Stanford PhD student at the time the package was created. The team published a paper in 2017 titled POMDPs.jl, a framework for sequential decision-making under uncertainty, with credit given to Maxim Igorov, Zachary Sundberg, Edward Balaban, Tim Wheeler, Jayesh Gupta, and Michael Kochenderfer. I apologize if I mispronounced any names. POMDP stands for Partially Observable Markov Decision Process. POMDPs.jl is not a single Julia package, but instead, it's an interface that works with an ever-expanding universe of complementary packages that are under active development by a lot of folks, many of whom have a Stanford connection. There's a great tutorial playlist for the POMDPs.jl package on Julia's official YouTube channel, hosted by Robert Moss, who is currently a PhD student at Stanford. There's a link to that playlist in the description below. Just a fair warning though, POMDPs.jl is not for the faint of heart. This is definitely not a beginner-level package. It's an intermediate to advanced level package that is still under active development. You can use the PalmDPs.jl ecosystem for many different applications, but we're going to use it today in order to implement and solve an MDP. For this section, knowledge of Julia and VS Code is required. I'm also assuming that you're watching this entire machine learning playlist. In your VS Code Explorer panel, create a new folder for this tutorial. In the tutorial folder, create a new file called rl_mdp.jl. Launch the Julia REPL by using Alt-J, then Alt-O. Maximize the REPL panel. In the REPL, change the present working directory to your tutorial directory. Enter the package REPL by hitting the closing square bracket. Activate your tutorial directory. Add the following packages: Discrete Value Iteration, PalmDP Model Tools, PalmDPs, and Quick PalmDPs. When adding these packages, pay close attention to the uppercase and lowercase spellings. PalmDPs uses uppercase POMDP, but uses a lowercase s. Type in status to confirm the version numbers. Exit the package REPL by hitting backspace. For this tutorial, I'm going to dock the REPL panel next to my editor. Okay, let's take a look at a motivating example. Today's motivating example is inspired by an example found in the textbook written by Stuart Russell and Peter Norvig called Artificial Intelligence: A Modern Approach. I've modified the example slightly for this tutorial. The actual code for this example comes from Robert Moss's tutorial on MDPs. I've modified his code slightly in order to simplify it a little bit for this tutorial. So here's the basic setup and objective. Our world, or environment, consists of a 12-tile grid with 3 rows and 4 columns. Each tile is identified by an XY pair with tile 1, 1 in the lower left corner and tile 4, 3 in the upper right corner. In this environment, we're going to place an intelligent agent. Let's call him Agent Doggo, that can move from tile to tile. But when the agent moves, there's some uncertainty. For example, if the agent needs to move up, there's only a 70% chance that the agent will actually move up. There's a 10% chance that the agent may move left, and a 10% chance the agent may move right, and there's another 10% chance that the agent may move down. Also in this environment, there are a couple of rewards, one positive and one negative. The positive reward is a Doggo biscuit worth 10 points, located at tile 4, 3. The negative reward is a lava pit worth negative 100 points, located at tile 4, 2. And just to keep things interesting, there's an obstacle located at tile 2, 2 that the agent cannot pass through. Also, the agent cannot move beyond the borders. So if Agent Doggo starts at tile 3, 1, which path should he take in order to get to the Doggo biscuit? Intuitively, you might think that the agent should take the shortest path. But then there's a slight risk that the agent will fall into the lava pit. The alternative is to take the long way around, which is safer, but will take more time. So what should Agent Doggo do? This is a classic example of decision-making under uncertainty. Let's see how we can use the POMDPs.jl package to solve this problem. First, we need to load our packages. Since the POMDPs.jl package is really just an interface, we need to load several additional packages in order to use it. The additional packages that you need to include will depend on the problem that you're trying to solve. The actual solver is stored in a separate package. That's because there are many different solvers that you can use with the POMDPs.jl interface. The solver you choose will depend on the problem that you're trying to solve. Next, we need to define a custom data type for the state. In our diagram, each state is the same as each tile, which is identified using an XY pair. Next, we need to define a data type for each action that our agent can take. The @enum macro is from Julia Base. It creates a new data type for action. If you look in the REPL, you'll see that action contains the 4 directions along with an index number. For some reason, Julia starts the index at 0. Okay, let's move on to defining the state space. The state space is just a collection of the 12 tiles plus 1 additional tile for something called a null state. The null state is used to end the game. If you look in the REPL, you'll see that this code created a vector of all of the individual states. Next, we need to define the action space. You may be wondering, didn't we just do this? Well, no. When we used the @enum macro, we were setting up a new data type called action. Here, we're placing the individual actions into a vector of type action. Next, we need to define the transition function. This is the function that governs how the agent transitions from one state to another state given some action. I'm not going to lie, this bit of code is the most difficult part of this tutorial, so brace yourself. We start by setting up a dictionary that maps each action to a new state, which defines movement. So that wasn't too bad. Now we need to add a new method to the plus operator so we can add a current state to a movement in order to get a new state. So that wasn't too bad either. Now comes the tricky part. This is where we need to define a transition function T given a state S and an action A. The deterministic function is from the POMDP modeltools.jl package, and according to their documentation, the deterministic function is intended to be used when a distribution is required, but the outcome is deterministic. So in this case, the variable null is state -1, -1, which is used to end the game. This code will end the game when the agent lands on a tile with either a positive or negative reward. Next, we need to initialize some variables. Next_states is a 5-element vector initialized with undefined values. This vector will be used to contain the states needed for decision making. Element 1 is the current state, and the other 4 elements are the 4 possible new states. Probabilities is also a 5-element vector, but initialized with zeros. This vector will be used to contain the probability distribution of the agent moving in any given direction. This next section is the heart of this function. This code determines how the agent actually moves inside the environment. By using this code, we're saying there's a 70% chance that the agent will move in the direction that it's supposed to move, but a 10% chance for each of the other directions. The if-else-if statement in the bottom half blocks the agent from entering tile 2, 2. It also assigns probabilities for movements within the borders. This next section handles attempts by the agent to move outside of the borders. This code makes the agent bounce off the border and remain in its current state. This final section returns something called a sparse categorical distribution using the sparsecat constructor from the POMDP modeltools.jl package. Sparsecat assigns the probabilities contained in the probabilities vector to the states in the next states vector. So that's a lot of code for just one function. If you're going to make a mistake anywhere in this tutorial, there's a good chance that it will be here when creating the transition function. So be sure to double-check your code. You can find all of my code in my GitHub repository. There's a link to it in the description below. The transition function is unique to the problem that you're trying to solve, so there's really no way to generalize it. Being able to write this code will test your general coding skills using Julia. So now you can see why I consider this an intermediate to advanced subject. The good news is that the rest of the code is not as tricky. Next, let's define the reward function. This code places a negative reward of -100 in tile 4, 2 for the lava pit, and places a positive reward of +10 in tile 4, 3 for the doggo biscuit. Otherwise, the reward in every other tile is 0. Next, we need to assign a value for the discount factor gamma. You may have heard the cliché that $1 today is worth more than $1 tomorrow. That's the idea behind the discount factor. It places a higher value on near-term rewards and places a lower value on future rewards. I'm using a value of 95%, but you can use any value between 0 and 1. Next, we need to define the MDP by using the Quick POMDPs package. As part of the definition process, we need to define a function that returns a Boolean for whether or not the state is the null state. We also need to define a custom data type for our environment, which we're calling GridWorld. Finally, we use the Quick MDP constructor to create our MDP. You'll recognize most of the arguments from the mathematical definition of an MDP, which is a 5-element tuple consisting of S, A, T, R, and gamma. Using Quick MDP creates the mathematical framework that we can use to run through an algorithm in order to quote-unquote solve it. We're going to use a solver from the discrete value iteration.jl package, which is an implementation of the value iteration algorithm. You can play around with a maximum number of iterations, but 30 is fine for this example. As a reminder, the value iteration algorithm uses an iterative process in order to calculate the value for each state using something called the Bellman equation. The Bellman equation calculates the value of each state as the sum of an immediate reward plus the discounted sum of all future rewards. By using this equation, the value iteration algorithm can figure out the optimal values for each state that maximizes the reward. Based on those values, the algorithm can then generate an optimal policy that maps each state to an action. If you look in the REPL, you'll see the actual policy. As you can see, each state is mapped to an action. Let's take a look at this policy applied to our diagram. So according to this policy, if Agent Doggo starts in tile 3,1, then he should take the long way around in order to avoid the lava pit. By using this quote-unquote treasure map, no matter which tile our agent starts at, he will know the optimal path to take in order to get to the Doggo biscuit. Pretty cool, right? Now, how did the solver know which actions to assign to each state? Let's go back to the editor and generate the values for each state. The variable policy has several different fields, one of which is called util, which is short for utility. Utility is another name for the values. If you look in the REPL, you'll see values associated with each state. By using these values, the solver can determine the actions to take in order to maximize the potential reward. Let's take a look at these values in our diagram. Now that we see the values, we can understand why it told the agent to go the long way around. State 3,2 has a negative value since there's a 10% chance of falling into the lava pit if the agent tries to move off that tile. State 4,1 also has a negative value for the same reason. Pretty amazing, right? We covered a lot of material in this tutorial, so let's break here and go through a recap of what we just saw. Today, we took our first step on our reinforcement learning journey by learning about the Markov decision process, or MDP. An MDP is a mathematical framework for sequential decision-making under uncertainty. Mathematically, an MDP is a 5-element tuple containing S, A, T, R, and gamma, where S is the state space, A is the action space, T is the transition function, R is a reward function, and gamma is a discount factor. We solved our MDP using the value iteration algorithm, which uses the Bellman equation to figure out the optimal values for each state that maximizes their reward. The result was a policy that mapped each state to an action. By using this policy, our intelligent agent was able to determine the optimal action to take given any state in order to obtain the maximum reward. That's a lot of concepts and code for one tutorial. In the next tutorial, we'll build on this MDP foundation and get a proper introduction to reinforcement learning. Well, that's all for today. If you made it this far, congratulations! If you enjoyed this video and you feel like you learned something new, please give it a thumbs up. For more wholesome Julia tutorials, please be sure to subscribe and hit that bell. If you like what I do, then please consider joining and becoming a channel member. New tutorials are posted on Sundays/Mondays. Thanks for watching, and I'll see you in the next video.